Okay, well, after that exciting setup, so we're really pleased to have Dihua Jiang from the University of Minnesota. Will tell us about Shalika periods, Functoriality and Arithmetic.
Thank you very much. I enjoy this program very much, and thank you for the invitation to give a talk here. So the period is like popular in this program, right? So, but I sort of take one particular period and then talk about where it started working, you know, how we introduced it, and then developed, and we'll go into this BZSV program. And then by the end, I'll mention also the recent applications of this period to arithmetic problems, you know. So in this sense, that the one period can have a very deep impact to the subject. Okay. Okay, so Shalika period. So this is very simple, just GL2N, and you take the parabolics with Levy GLN, and the unipotent radical is abelian, right? And then you fix a character, which is a-adic modulo rational. And then according to the Pantchagan duality, the character of this n-adic modulo n rational given by a matrix A, the same size, right? And then the correspondence will be the character psi A is given by the trace of the A transpose, because this is like a killing form duality, right? So the character is a coadjoint orbit, right? So that's the things. And then since this is a pretty homogeneous space case, so that the finite orbit, and then the Zariski open orbit is given by the identity. And so this gives you so-called the generic characters. Yeah, so we specifically take, you know, representatives that take A equal to IN. And then you stabilize, you consider the stabilizer. This is like always the setting, right? I think this kind of setting go back to like a Mackey theory, right? So there is like a Mackey induction, like a Katang motion group. I think that was the earliest setting like this, okay? But now we are sort of in more general setting, but less complete story. And the stabilizer is the diagonal embedding of GLN. And so you take this semi-direct product, the unipotent radical and the stabilizer. So the element writes NX H diagonal. So you define the one-dimensional representation or function like this, which is on SA and left SK invariant. And so you use this data to define the Shalika period for any automorphic, cuspidal automorphic. Well, you can define for any automorphic forms, but you know, there's a convergent issue, but for cusp form, this safe, right? So there's indigo convergence, so you define this. So this is what's so-called the Shalika period. Okay. And so the Shalika period was first introduced by Jacquet and Shalika, a 1990 paper to construct zeta integral for exterior square L function. And so here is the theorem. So a cusp form on GL2N, and this Shalika, the exterior square L function, holomorphic when real part S positive, I mean greater than 1. And then the following three are equivalent. So if this L function has port 1, and the pi is the Langlands transfer from sigma from G spin group, that's because of the character, the twist here. Okay, the twist. And then number 3 is pi has a Shalika period. And so this theorem is like the most general version this type. But historically, it was proved in the special case first, noticed the chi equal 1. Okay. The proof of this special case, chi equal 1, in this case, you don't need a G-spring group. So in this case, the sigma, the Langlands transfer, so the twist endoscopy will be just SO 2n plus 1. But this uses almost all the work previous done. Yeah, originally by Jacquet, P.S. Shalika, 1983 paper, Langlands-Symplectic convolution. And then you also use Langlands-Shahidi method to normalize the Eisenhower series involved. And then, of course, Jacquet-Shalika integrals, and then Cocktail, Piatetsky-Shapiro global converse theorem, and then Ginzburg-Rales surgery automorphic descent, and then surgery myself local converse theorem to show that this Langlands transfer, to show two things. This sigma from this construction is irreducible, and then the Langlands transfer is matched compatible with local Langlands every place. Okay, so this is sort of this accumulation for so many papers. But I think for chi not 1, I think it's remain to be done. This theorem, I like the theorem, but if chi is not 1, I think there's partial progress by many people. I didn't list the name here, but it's not complete yet. Okay. This is nice sort of pattern as a theorem, as a model. So you try to see period, L function pole, and the functoriality, how it relates. Okay. Okay, and then Friedberg and Jacquet 1993 paper is the first time to use this Shalika period to construct a different L function. So he introduced this integral GLN, this H1, H2 are all GLN. They're gonna like a levy, right? So this is the so-called linear period. So in other words, Jacquet Shalika showed that the linear period is holomorphic, well-defined. Also, when the real part is S large, you can unfolding to this Shalika period integration. Okay, so this is like a very nice generalization of Jacquet Langlands original GL2 version, right? In GL2 case, the H1, H2 will be just GL1, right? And then you take out the central character will be A1, right? Just we take 1A and 1 here, okay? And Shalika period is just reduced to Witten one, right? So Jacquet Langlands is like a torus integration unfolding to Witten, right? But so this is like a nice generalization of that to GL2N. Yeah, they're perfect. Okay. And so, but the local version of the relation between the two periods was first discovered by Jacquet-Rales paper, but this is only local. Yeah, for p-adic, he discovered the relation between two periods in 1 year earlier. And then in the Archimedean case, Eisenbach, Gravich, and Jacquet did the real Archimedean case, the local relation of the two periods. Okay. And so the theorem of Jacquet can be summarized like this. So pi is cusp form. If it has Shalika period, if and only if pi has a linear period plus the central value non-vanishing. Yeah, so in other words, the two periods globally, they're not equivalent. The one is weaker by a central value non-vanishing. Okay. Of course, you can write the theorem 1 in terms of linear period in theorem 3, right? Replace the Shalika period by linear period, but you add this central value non-vanishing condition. Okay. Of course, there is a story about the period when it's you have to prove local multiplicity 1 theorem, and there is a special case was proved by Jacquet, Wallace, and my student Yang things, but the most general was very recent proved, right, by Furui Chen and Bingyong Sun, 2020. It was surprised, right? So the period was studied a long time ago, but this is one of the fundamental results that we need was, but in this generality was proved just recent. Okay, so for the p-adic case, you can also have these relations, right? For p-adic, you prove like you replace cuspidal by supercuspidal, and then L function replaced by gamma factor, and then the same kind of theorem can be proved. And the relation between Shalika period and linear period, Matrin proved to 2013. For unitary discrete theories, they can prove equivalent. Yeah, we can prove supercuspidal equivalent. It's relatively easy, but for discrete theories, it's a little bit more work. I think we expect this is true for tempered, but not proved yet. Yeah, so I think according to your conjecture, probably they expect this should be true for tempered. Okay. So in other words, although this period, this is like a period next to Whittaker period. Whittaker period we know a lot of work is based on Whittaker. This is the one just next to that, but still many things going on. Okay, so I try to put the whole theory related developed into this beautiful diagram. Okay, so this diagram is like a G. We are talking about the cusp-forms or supercuspidals in this GL2M, right? And you cut, this is like a mirror symmetry, okay? Yeah, so this side is like a Bessel period, either local global, okay? And this side is a linear period, okay? I will explain some details, but I just explain this diagram first, okay? And so LQ means you do parabolic induction and take a Langlands quotient. So LQ, you do the same thing, okay? And this is Langlands transfer, right, from other circular group. And this is also Langlands transfer, okay? And then this will be Bessel descent, ED, and then Fourier-Jacobi descent, okay? And this TC is theta correspondence. Okay, so this diagram is commuting, whatever you go. Yeah, so it's all related, right? Yeah, so in other words, this theta correspondence takes Bessel model to linear model. Okay, here we figured out that like a generalized Bessel Shalika period. Okay. And here will be symplectic linear period. Okay, so theta correspondence switch this generalized Shalika period to symplectic linear period. Okay, I think for the symplectic linear period, I think Omar was talking about more general like this. Yeah, so this diagram actually also accumulates many people's work, but I didn't write it. So all the names, you know, contributes things. Okay. So globally, again, this commuting diagram works if the central value is non-vanishing. But for p-adic, you assume supercuspidal. But I expect that, as we claim that, for temporal representation sure works same, but not approved yet. For supercuspidal or cuspidal with central value non-vanishing, you can do this. Okay. Any questions? You can do it with global, but you can also do it purely local. Yes.
What is meant by the decimal set of the British cookies?
Oh, I'll explain. Yeah. So I just here just a framework, right? Okay. So now let's explain this in terms of BZSB. Yeah. So you have GL2, the data, right? You know, you can call the spherical variety or the data or the like a Tian was talking like a triple or quadruple, like, you know, and then you have a dual group attached, right? And so for tempered as a parameter, and then the Shalika period, well, if only if the Langlands parameter, right, will factor through this symplectic, right? So this is why the previous page, you know, you have Shalika period and then leaf from here. The dual group of this guy is the SP, right? So this is why that. Okay. Actually, this theorem was confirmed for supercuspidal in my paper with my student 2008. Yeah, but we expect this for tempered also true, but for tempered it's still open. Yes. Who proved that?
Okay. So how do you reduce the discrete series and
I don't think so. I don't think it's proved. Yeah, maybe. Yeah, I think for tempered, I don't know who will be possible doing that. Okay, you check. Good. Okay, so now I explain this kernel. Yeah, so this SP4N. So SP4N, you have maximum parabolic with Levy subgroup GL2N. And then you, again, the unipotent radicals are abelian. And then you have a similar kind of character, which stabilizer now because SO2M, the unipotent radical is skew symmetric, right? And the skew symmetric stabilizer will be symplectic type, right? So this is why the generalized Shalika group will be looks like this. You have the reductive part is symplectic group, and then you do the same thing, right? So you induce from the Levy, and then you put when the exponent is half, you know this is reducible and has Langlands quotient. Yeah. So this representation will be Arthur type. Yeah. And then in 2008 paper, I did it with my student. And we proved that you know, the Arthur parameter now you have this SL2 part. So you factor through like this. Okay. So again, this triple the data will be the dual group of that will be SP 2n. Okay. Okay. So now we try to write this in terms these quadruples. Yeah. So for the SO4n, and then you have the data like this, right? So because this is Shalika period, generalized Shalika period, like that, and then this period is self-dual, like the same, and then the GLN part is Shalika period, is this data, and the dual data is like a functoriality from this. Okay, and so from the dual side, the transfer is basically the Whittaker induction of spherical writing in a sense, or Whittaker induction of the data, like that. Okay, and then the other orthogonal part, you take a generic, right? So because of the Whittaker model, this is regular orbit here. Okay, and then the dual side will be because it catches the temporal spectrum, so it's given like this. And then this is the Langlands transfer of the temporal data by the dual side, like that. Okay. And the other side will be, symplectic situation. And so the period of SP will be SP2n times SP2n, right? So that's like a symplectic linear period. And the dual will be transfer, right? So the transfer is like that. And then GL linear period, right? And then the linear period will characterize the spectrum. And so again, this is the Whittaker data, Whittaker induction. And then for SP tilde, you get a generic guy, it's like this. And the dual side is for the temporal data. So that the transfer for Langlands like this. But of course, the quadruple I'm talking here, including the covenant group. Yeah, so that's.
The local, one direction was approved by Shiva, the theorem of the chunk. The other direction was approved by Lapid and Mount.
For Shalika tempered.
So for discrete series, the tempered follows from the chunk result for the wind type.
Oh, okay. So this is good. This is known. Very good. Okay. So now I explain this automorphic descent of Bessel type, and the Fourier-Jacobi is the same kind, right? But just okay. So I'll not try to introduce the most general situation. I'll just show you the examples. Okay, so you take a unipotent subgroup. So Z is the upper triangular of GL n-1, okay, like this. Of course, you can use, general setting, the descent, you guess, like inner forms and things, but I just try to take as simplest as possible here in the talk. So you take a character like this. Okay, so basically up to here, you realize this is like a Whittaker character in this Z part. Okay, and then there's the X part. Basically, you take an isotropic vector here, which is, it's Zariski open orbit. Okay, so you have generic. Okay, and then you take a stabilizer of this. Again, this stabilizer will be SO2n plus 1. So if you take a different anisotropic orbit, and then you can get rational forms of this guy. Okay, so in other words, this descent you can construct automorphic representation for inner forms. And this is compatible with global Gang-Grossar conjecture. Yeah. And so you take a Fourier coefficient like this, and so this will become automorphic function on SO2n plus 1. Yeah. Yeah, so the thing is, what is this? What is this automorphic functions? We want to understand. Okay, so Ginzburg, Wallace, Sudbury, 2003 show that sigma is non-zero cuspidal automorphic representation SO2n plus 1 you created by the Fourier coefficient, right? It is this, right? Sigma is you correct these functions. So you show that this cuspidal automorphic and transfer to tau you start with, I think it's pi. It should be pi. Okay. At almost all finite places. And then I prove with surgery that this sigma actually is irreducible. Yeah, so this takes a while to prove. And also Langlands transfer is compatible at all places. That's also it's a lot of work you have to do it. Okay. So, but this construction can be formulated and proved for all quasi-split classical groups. Yeah. And this is in their book, Ginzburg, Wallace, surgery book, 2011. And so this construction can be extended to like non-quasi-split groups, or even more general. You know, this is like a special type of endoscopy, right? You can do general endoscopy by integral transforms. Yeah, we can formulate this. And so this is a formulation I think you can find in my paper in PS memorial volume. And Ginzburg has some special cases. And then I did with my student Lei Zhang, so he is now in Singapore. Extends this is a special case of this my 2014 paper, but more general than GRS, and so that will general enough so that we can prove apply this method to global gangulus Poisson conjecture. Okay, it's nice. But to tell you briefly a flavor of what is endoscopic transfer by integral transform. So basically, if you have the endoscopic group like a G0 and H, is endoscopic G. So you expect a transfer from alpha packet to the alpha packet, right? So this is what for classical group, this is what also proved. Okay, also proved the existence. Of course, they have these character relations. Yeah, but we want to show that there is, there's an automorphic kernel, so that this gives you transfer like theta correspondence, right? So, yeah. So the idea is this. So I use the information from G0 to build a kernel function. This kernel function only depends on G0. But in the theta correspondence situation, the kernel depends on a character, right? So in other words, it's a sort of GL1 information, right? So now you have bigger, you have like a cuspidal information there. Okay, but still you can construct. But this kernel is given by Fourier coefficient of certain residual or Eisenhower series. Yeah, so, but in the big group, right? You go to the big group and take a small representation, right? V representation also as a quotient of induced representation, right? You can realize V representation as a quotient. Yeah, so it's a similar feature. Similar feature. So you build this kernel function, and then you show that if such integral, now see this kernel you have stabilizer. Yeah, this kernel is built on H times G, right? So you have three things, G0, H, and G, and you put this G0 information to build the kernel and the relation between H and G, right? And so as long as the integral non-vanishing, you expect the H will transfer to G, of course G also transferred. It's both side relation, right? And so the other parameter is, the parameter G is the H parameter plus the G0 parameter. And then vice versa, you just subtract, right? You just subtract that component. Of course, this is conjecture. Yeah, so we can prove some cases, but in general, this is still conjecture, right? But it's in my paper, 2014. Yeah, so but at least you see there's a hope. The endoscopic correspondence actually is integral transform.
Is there a conjecture where these how to construct the kernel function?
Yeah. I write down the kernel can be written down explicitly. The only thing is if the integral non-vanishing, you want to show that, yeah, this is a cusp form, right? This is a cusp form. You put the integral non-vanishing, and then the key point is you want to see the parameter match, right? Yeah. Any questions? All right. Okay, so now I'll talk about the arithmetic side of the Shalika period. I think I have 20 minutes. So we started doing this, quite sort of relatively recently. But this originally, these things go back to, see, right after the Shalika period was sort of used in the theory. It's 1994, right? So there was 1990 was Jacquet Shalika, and then there's Friedberg Jacquet 1993, right? So they realized, okay, this integral, this period has potential arithmetic. So H, and David Ginzburg to work on this related to GL2 and p-adic L function. So you have to construct the p-adic L function. But they, in their construction, they have assumption like as a modular symbol at the Archimedean place associated with the Shalika period should be non-vanishing. Yeah, so this is like a generalized modular symbol. Yeah, because Shalika period is not reductive, right? So for the all reductive subgroup, the modular symbol was like a very major was studied in the 70s. There's notes, but not published. Yeah, so I think you can still online say probably you can figure it out. I figured it out, but somewhere, yeah, very has these notes. And then later, I think Borrell, Evner, Ash write more papers about this more general modular symbol what it looks like. Yeah. But anyway, so they need such Archimedean non-vanishing of this modular symbol to show that this p-adic L function is there. Brognan and Langlands 2014 paper tried to formulate the approach to see, the critical L value modulo certain so-called transcendental period and will be algebraic. So this is kind of result. Okay, so this result of course originally go back to the Shimura GL2, long time ago, and Harder and Manning, they all have this work for GL2. Harder, I think Hida has some GL2 times GL2. They are all long time ago. And so for higher rank, there's nothing. Of course, you have the link conjecture if the automorphic is motivic, and then you have the link conjecture 1979, right? The Corvallis, they have these formulations. But nothing really can be proved. So they good. They find a way to do this. But unfortunately, I think a few years later, Grabner show that the argument has some technical gap. I try to make it up. So he wrote a paper, a recent paper with my change and did some improvement, but still not cover sort of general situation. And then there's a young guy came up, Generalizations. He developed a different kind of things like a rationality or horizontal module, all things to show that this Grabner Langlands work can be so that these issues can get along, but still he needs the assumption that existence of universal homological test vector. I'll explain to this. So you need this. So in other words, for the L function you have different critical values, and then you can have different period. So these periods are not independent. Okay, but in order to show that they are not independent, you need this assumption. To relate one critical value to the other. So otherwise you just one of the curiosity from the transcendental number theory point of view, how do you explain the transcendental number, right? That's like one of the toughest question in number theory, right? So how do you understand this? We only understand pi or something, right? Right. So L function is supposed to produce more transcendental number. So what is this, right? So this is of course you have period which attach modules, right, like this. So this is theorem. We light up the proof of 2019, and then the pandemic and delayed and revising things. But so the first version was on archive 2019, and now recently we have final revision of that. So the theorem is like this. So you have, if you have GL2M cuspidal, and then you assume this is regular algebraic. So that's the standard assumption from the motivic point of view. Like automorphic, if you relate to the geometry, sure. This is Closier's work, right? Show that the automorphic representation of GLN come from the motivic must satisfy these two conditions. Okay, so for these guys, and then you have this Shalika period, and then the theorem will be like this. So you have quite many critical values. So assumption is the coefficient system is balanced to guarantee that there is critical value. Okay. Under this assumption, and so you have this period. So I'll explain here. So the Gauss sum you have to divide, and some number divide, and then this is the cohomological Shalika period associated with pi at the infinity. And so after that, this will be in this field which so-called rational field or cusp form of these characters, like that. That's exactly the generalization of Shimura work from GL2 to GL2M. Okay.
What is it? Theta?
What? Theta. Theta is the character come from Shalika period. The chi is the twist. This makes this theorem like a most general situation. Okay. And now I try to explain a little bit more about what this theorem is about. Okay, we go back to the Friedberg Jacquet local integrals. Okay, so you have this local version, right? Shalika functionals, and then you define the Shalika function. And then the local Friedberg-Jacquet integral looks like this. You use the Shalika model to do integration. This is, yeah, again, this n, if n equal to 1, and this is like Hecke integral, right? So the S become a Whittaker model, and then the A1, and then character. Yeah, exactly the same. Okay. And so the first property, they show that there is a unique functional from pi with parameter goals. It's holomorphic in S. When the real part of S is sufficiently large, and this functional can be realized as a normalized local Friedberg-Jacquet integral. Yeah, so in other words, the Friedberg-Jacquet integral divided by the twisted L function locally. Yeah, so that's what would be, as long as the real part is large, so you get this functional normalized. And number two, and then you show that this, if you take a character looks like this, and then this normalized Shalika, normalized the Friedberg-Jacquet actually produce a linear functional locally. Yeah, so like this. And you can choose a vector in pi such that this is not normalized, so that this is 1. Okay, this is the test. This is so-called the test vector. And then for non-Archimedean, yeah, so this will be polynomial type. Yeah. And in particular, for unramified data, this will be automatically 1. So that you can take an Euler product, because almost everywhere 1, you take a global things. Okay. But the question for arithmetic application, the question is, you have to pick up this U has something to do with the cohomological vector. Yeah, so that's really the test. Yeah, in order to get you know arithmetic operation, you need to go dig very deeply to do this technically. Now here is the assumption. So you assume this pi is algebraic and regular in the sense of Closel, and has Shalika period. For this talk, we can just simply take K equal to Q. It works for general algebraic numbers. And Closel showed that under such assumption that this Archimedean component will be regular algebraic and the essential temporal cohomological. Yeah. And then Closel and Chenevier, yeah, that's a more recent work. They show that all this essential temporal cohomological representation of GL2N will be symplectic type. Yeah, so this is what they prove. And then we show, in our paper, we show that, so this representation will be parabolically induced from the GL2 discrete series, right? The GLN has no discrete series, but GL2 has discrete series. But this is the representation will induced from the GL2 Archimedean part. Yeah, so that's a nice structure. Very important because, and then so in order to formulate this, representation is cohomological, you need a coefficient system. So this is a finite dimensional representation of the dual group. Yeah, so, and then you cohomological non-vanishing, right? It means you realize in the continuous cohomology. Here, non-vanishing. And so the point is these characters has a pattern and satisfies this twist dual relation. This is Closel show that this must be looks like that. And then the sigmas will be essentially square integrable with the character, infinitesimal character like this. And then the critical point can be computed in terms of pole or the local gamma factor in the Archimedean. And so which is like half integer, looks like this. Okay. And then we show that for these local places, yeah, there is this is a rational field determined by pi or the character. Yeah, there is such a rational structure on this representation. Yeah, so that's essential. And then this is normalized the Jacquet Friedberg Jacquet integral modified by the Gaussians. The Gaussian contributes from the non-Archimedean part, where lives in this Helm space. Okay. So and then for anonymized this, of course, yeah. So the data will be chose in this rational with the rational structure. Okay, and then this is like a more property of the rational structures. Yeah, so this is rational structure. Yeah, so one of the technical gap in Grabner Langlands paper was the proof of this. Yeah, so of this important structure. And now let's deal with the Archimedean. Yeah. So Archimedean, assume you have this, take a lambda infinity Shalika functional, and by Vaughan 1986. And then this pi has a unique minimum p-type, tau infinity. Yes. We show that with respect to this minimum p-type. Yeah, so in other words, you have this Helm space non-vanishing, and then you can construct. We actually explicitly construct this vector by invariant theory. Yeah, it's like an Archimedean invariant theory to explicitly construct this vector such that this normalized Friedberg-Jacquet integral for this particular vector, which is uniformly equal to S for NS. Okay. Yeah, this I think this kind of result was tried by Eisenbach, Gravich, Jacquet 2009 by they constructed a vector with this property, but they even don't know that this vector is K finite. Yeah, that's like a way, for arithmetic application is way not enough. And then Ben-Yongsun move up. Well, he constructed a representation, the vector, this particular representation in K type, but it depends on S. So for each S, he construct one. Yeah, it's not a uniform for S. But for as I explained that, for uniform for S, will explain that the different critical value, this period are related. That's essential towards this conjunction. Okay. So now Ginzburg, Ginzburg non-vanishing assumption basically is introduce the modular symbol, which is a composition of this so-called canonical map. But by the end, you have to show that its composition is non-zero, right? But we prove this based on our construction of this vector, particular vector. Yeah, so that saves us. That's important. The local period relations, yeah, so the different period, actually, you have this identity like this. Yeah, so this is modular symbol. Yeah, this is the relation which take as assumption in Generalizations work 2016. Yeah, so we get it. And now you have to interpret Friedberg Jacquet integral in terms of cohomological structure. Okay, so in terms of cohomological structure, this local integral can be interpreted as this commuting diagram, right? So the integral has an interpretation like from the linear period unfolding to Whittaker period, right? And so this unfolding has this cohomological interpretation and becomes a commuting diagram. That's very important. Yeah, so that's important. So you get this, and then this Ginzburg Ginzburg assumption can be deduced from the existence of universal uniform testament. We prove. Okay. Yeah, once you get this, and then you show that okay, there is a cohomological class which evaluated this modular symbol, evaluated this class is non-zero. So that's essential, right? So once you get this, and then everything else will be deduced from comparison of these rational structures we introduce. And you get the algebraic number, right? So that's it. Thank you.
Very much. Questions? A very big question. The construction that you from your 14 paper, there's the integral transforms. For endoscopic. So can you think of that construction as a construction of from this point of view of duality of periods? Is there a way of thinking about them as the integral kernel itself as some period?
Yes, that's a good question. I talked with Chen Wang. The first 2 days here, we sort of get stuck. This construction has this kernel. It's hard to sort of explain because the kernel is a very degenerate cusp forms. Right. So you make SL2. Yeah, SL2. Right. This SL2 in the current framework, the SL2 representation is sort of limited, right? But I think this construction of this kernel is go way beyond that. Yeah. So that's one of the problems. I think. Yeah, we'll think about it. That's a good question. We are sort of in mind. Anyway, it's a sort of the functoriality depends on period integral non-vanished, right? That's the same philosophy, right? It's your philosophy about this, right?
Thank you very much.
Thank you. Yes, no question on Zoom.
They tend to be very quiet on this.